So here's something worth thinking about as you settle in tonight. Right now, as you're lying there, you're moving. Not just the gentle rise and fall of your breathing, not just the slow rotation of the Earth carrying you eastward at maybe 1,000 miles an hour, depending on your latitude. You're also swinging around the sun at about 67,000 miles per hour, and the sun itself is drifting through the Milky Way at nearly 500,000 miles per hour. And the galaxy is falling towards something called the Great Attractor, at a speed that's frankly absurd to even think about. You're stacked inside all of these motions at once, like a passenger on a train who's walking down the aisle of a bus that's driving along the deck of a ship. And you feel none of it. Not a whisper. The smoothness of it all is, honestly, one of the most remarkable things about being alive, and most of us never give it a second thought. But tonight, let's give it a few thoughts. Let's talk about the solar system. Not in a rushed, textbook kind of way. Let's just wander through it slowly, starting from the very beginning, from before there even was a solar system, and see how all of this came together. Because the story of how we figured out what's going on up there, how we went from thinking the Earth was the flat, fixed center of everything, to understanding that we live on a medium-sized rocky world orbiting an ordinary star in one arm of a spiral galaxy. That story is one of the great human achievements. And it took thousands of years, and it involved some of the most brilliant, stubborn, wrong-headed, courageous people who ever lived. So let's start there. Imagine you're someone living maybe 5,000 years ago. Could be Mesopotamia, could be Egypt, could be China, or the Indus Valley. You're an agricultural person. Your life depends on the seasons, when to plant, when to harvest, when the river floods. And you notice, because humans are pattern recognition machines, that the sky is not random. The sun rises in roughly the same part of the horizon each morning, but not exactly the same spot. It drifts. In summer, it rises farther north, arcs higher across the sky, stays up longer. In winter, it swings south, stays low, and the days are short. And this pattern repeats, reliably, year after year. That's not nothing. That's a clock. That's a calendar written across the entire dome of the sky. And if you can read it, you can predict the floods. You can time your planting. You can prepare for winter. So people started paying very close attention. The Babylonians, in what's now Iraq, were extraordinary at this. By around 1800 BCE, maybe earlier, they had systematic records of celestial events. They tracked the moon's phases with remarkable precision. They knew that lunar months were about 29.5 days long. They built a calendar around it. They recorded eclipses and eventually got good enough to predict them, at least roughly. And here's what's really impressive. They did all of this without any understanding of what the moon actually was. They didn't know it was a rocky sphere reflecting sunlight. They didn't know it orbited the Earth. They just knew the pattern. They were empiricists of the highest order, cataloging the sky's behavior the way you might catalog the habits of a river or the migration of birds. The sky does this, then it does that, and after this many days, it does the first thing again. Write it down. Tell your students. Keep the records going for centuries. And those centuries of records mattered enormously because patterns that take a long time to repeat, like certain eclipse cycles, only reveal themselves across generations of observation. The Babylonians had what we might call institutional memory. Scribes passing knowledge to scribes, clay tablet after clay tablet, stored in temple archives. One of the cycles they identified, called the Saros cycle, is about 18 years, 11 days, and 8 hours long. After one Saros period, the sun, earth, and moon return to approximately the same relative geometry, and eclipses repeat in a similar pattern. Figuring that out from raw observation, without telescopes, without any model of orbital mechanics, just from watching and writing things down. That's genuinely stunning. Now, the Babylonians weren't the only ones watching. The ancient Egyptians aligned their calendar to the heliacal rising of Sirius. That's the first appearance of Sirius in the dawn sky after a period of being hidden behind the sun's glare. That event roughly coincided with the annual flooding of the Nile, which was the single most important event in Egyptian agriculture. So the sky wasn't just beautiful or mysterious to these people. It was practical. It was survival. And that practical motivation is what funded and sustained astronomical observation for millennia. Kings and pharaohs didn't pay astronomers because they were curious about the cosmos in some abstract way. They paid them because accurate calendars meant efficient agriculture meant stable kingdoms. But here's where things get philosophically interesting. Alongside the practical sky watching, people also wanted to understand what was actually going on. Not just what the sky does, but what the sky is. And this is where the ancient Greeks come in. Because the Greeks, for all their flaws, and there were many, had this remarkable cultural habit of asking why, not just recording the pattern, but trying to explain the mechanism behind it. One of the earliest Greek thinkers to really grapple with this was Anaximander, around the 6th century BCE, from the city of Miletus, on the coast of what's now Turkey. Anaximander proposed something radical for his time, that the earth wasn't sitting on anything. It wasn't resting on the back of a turtle, or floating on water, or supported by pillars. It just hung there, in the middle of everything, held in place by symmetry. There was no reason for it to fall in any particular direction, so it stayed put. Now, his specific model was wrong in lots of ways. He thought the earth was shaped like a short cylinder, like a hockey puck, and that the stars and sun were actually holes in great rings of fire that encircled the earth, and we saw the fire peeking through the holes, which is wonderfully creative and completely incorrect. But the impulse to propose a physical mechanism to try to explain celestial phenomena without just invoking the gods, that was revolutionary. A little later, the Pythagoreans, followers of Pythagoras in the 5th century BCE, proposed that the earth was a sphere, and they had some decent reasoning. They noticed that during a lunar eclipse, the shadow the earth casts on the moon is always curved, no matter what angle the eclipse occurs at. The only shape that always casts a circular shadow is a sphere. That's a beautiful piece of observational logic. They also noticed that when you travel north or south, different stars become visible above the horizon, which makes sense on a curved surface, but not on a flat one. So the spherical Earth was actually an established idea among educated Greeks, well before Aristotle formalized the arguments in the 4th century BCE. This is worth emphasizing because there's a popular myth that people thought the Earth was flat until Columbus, and that's just not true. Educated people in the Mediterranean world had known the Earth was round for nearly 2,000 years before Columbus was born. Now, knowing the Earth is a sphere raises an immediate question. How big is it? And this is where one of my favorite stories in all of science comes in. Around 240 BCE, a man named Eratosthenes, who was the head librarian at the Great Library of Alexandria in Egypt, figured out the circumference of the Earth using a stick, a well, and some geometry. Here's what he knew. In the city of Sienne, far to the south of Alexandria, modern-day Aswan, on the summer solstice at noon, the sun was directly overhead. He knew this because sunlight would shine straight down to the bottom of a deep well without casting any shadow on the walls. But in Alexandria, on that same day and time, a vertical stick, a gnomon, cast a definite shadow. The sun was not directly overhead. It was about 7 degrees off from vertical. Now, if the earth were flat, the sun would be at the same angle everywhere at the same time. The fact that it wasn't meant the earth's surface was curved. And here's the clever part. Eratosthenes knew the distance between Cyane and Alexandria, roughly 5,000 stadia, a Greek unit of measurement. He reasoned that if 7 degrees of the Earth's curvature corresponded to 5,000 stadia, then the full 360 degrees of the circle would be about 250,000 stadia. And depending on which version of the stadion he was using, and historians genuinely argue about this, his answer comes out to something remarkably close to the actual circumference of the Earth, roughly 40,000 kilometers, with a stick and a shadow. In 240 BCE. Think about that for a second. That's the power of geometry combined with careful observation. No technology needed. Just a clear question and a clever way to answer it. And Eratosthenes wasn't working in isolation. The Library of Alexandria was, for several centuries, the intellectual center of the Mediterranean world. Scholars came from everywhere. They had access to Babylonian astronomical records, Egyptian calendrical knowledge, Greek philosophical traditions. It was a place where information converged, and that convergence made new insights possible. When we talk about the solar system, about how humanity pieced together the grand structure of what's out there, we have to appreciate that it wasn't one genius working alone. It was networks of knowledge built across cultures and centuries. So, by the time we reach the 2nd century BCE, the Greek astronomical tradition had produced something genuinely sophisticated. A man named Hipparchus, working on the island of Rhodes, compiled the most accurate star catalog of the ancient world, about 850 stars, with their positions measured to a precision that wouldn't be significantly improved upon for over 1,000 years. Hipparchus also discovered something remarkable called the precession of the equinoxes. He noticed that the positions of the stars relative to the equinox points, the places where the sun crosses the celestial equator, were slowly shifting over time. The whole sky was rotating, incredibly slowly, taking about 26,000 years to complete one full cycle. He figured this out by comparing his own observations to Babylonian records from centuries earlier. There it is again, that long chain of accumulated knowledge making new discovery possible. But here's the thing that dominated ancient astronomy, the big question that everyone was trying to answer, and that would take almost 2,000 years to fully resolve. What's actually moving? When you watch the sky, the sun appears to move across it during the day. The stars appear to rotate around us at night. The moon drifts through the constellations. And then there are these strange objects, the planets. The word planet comes from the Greek planets, meaning wanderer, because unlike the stars, which maintain their fixed patterns relative to each other, the planets move. They drift slowly through the constellations, generally going one direction, but sometimes, and this is the part that drove ancient astronomers crazy, they stop, reverse direction for a few weeks, then stop again and resume their original course. This is called retrograde motion, and explaining it became the central puzzle of astronomy for an extraordinarily long time. The most influential answer came from Claudius Ptolemy, working in Alexandria around 150 CE. Ptolemy synthesized centuries of Greek astronomical thought into a comprehensive model laid out in a massive work called the Almagest. In Ptolemy's system, the Earth sat motionless at the center of the universe. The moon, sun, and planets each rode on their own crystal sphere, rotating around the Earth. But to account for retrograde motion and other irregularities, Ptolemy added a brilliant mathematical device called the epicycle. Each planet didn't just ride on its main sphere, it also moved in a smaller circle, an epicycle, attached to the larger one. Imagine a point on the rim of a wheel that's itself rolling along the rim of a bigger wheel. By adjusting the sizes and speeds of these circles, Ptolemy could match the observed motions of the planets with impressive accuracy. And here's what you have to appreciate about the Ptolemaic model. It worked. It predicted planetary positions well enough to be useful for navigation and calendar making. It was mathematically elegant in its own way, and it aligned with common sense. You don't feel the Earth moving. The ground seems solid and fixed, and everything in the sky appears to revolve around you. For all of these reasons, Ptolemy's geocentric model became the dominant framework for understanding the cosmos for the next 1400 years. That's not because people were stupid, it's because the model was genuinely good at its job. And the alternative, that the Earth itself was hurtling through space, seemed to contradict direct experience. But there were cracks, even early on. The epicycles had to be tuned very carefully to match observations, and as observations got better, more epicycles had to be added. The system grew increasingly complicated, and there was a philosophical discomfort that some thinkers felt, a sense that nature shouldn't need this many gears to run smoothly. That discomfort would simmer quietly for a very long time, through the fall of Rome, through the preservation of Greek knowledge by Islamic scholars who translated and expanded upon it, through the slow reawakening of European intellectual life in the medieval period, and eventually, in a small city in what's now Poland, a quiet, cautious church administrator named Nicholas Copernicus would sit down and ask a question that would reshape everything. What if the Earth isn't at the center? What if the sun is? Now, Copernicus didn't arrive at this idea overnight. He was born in 1473 in the city of Turin, in Royal Prussia, and he was one of those people who just seemed to collect expertise the way some people collect stamps. He studied mathematics, astronomy, medicine, law, and canon law across universities in Krakow and then in Italy, Bologna, Padua, Ferrara. He was deeply embedded in the intellectual tradition of his time, which means he knew Ptolemy's model inside and out. He'd read the Greek texts, he'd studied the Arabic commentaries, and he understood exactly how the epicycle system worked. And it was precisely because he understood it so well that something about it bothered him. The thing that nagged at Copernicus wasn't that the Ptolemaic model gave wrong answers. It gave pretty good answers, actually. What bothered him was the aesthetics of it. The machinery felt too complicated. Too many little circles bolted onto bigger circles. Too many special adjustments needed to make everything line up. There's a concept in science and philosophy sometimes called parsimony or simplicity. The idea that if two explanations account for the same observations, the simpler one is probably closer to the truth. Copernicus had a deep intuition that the universe should be more elegant than Ptolemy's model allowed. So here's what he did. He took the sun and placed it at the center. He put the Earth in orbit around the sun, just like the other planets. And he let the Earth spin on its own axis once a day to explain the apparent rotation of the sky. And something remarkable happened when he did this. Retrograde motion, that weird backward loop that planets like Mars trace across the sky, the very thing that had required all those epicycles in the Ptolemaic model, suddenly had a simple, natural explanation. It wasn't that Mars was actually reversing direction. It was that the Earth, on a faster inner orbit, was overtaking Mars on its slower outer orbit. Think about driving on a highway and passing a car in the next lane. As you pull alongside, and then ahead of it, that other car appears to drift backward relative to the scenery behind it, even though it's still moving forward. That's retrograde motion. That's all it ever was. And you don't need a single epicycle to explain it. This is one of those moments in the history of science that gives you chills if you think about it long enough. A geometric puzzle that had tormented astronomers for over 1,000 years just dissolved. It wasn't a real phenomenon at all. It was an illusion created by your own motion, by our motion, by the fact that we're standing on a moving platform and didn't know it. Copernicus laid all of this out in a book called De Revolutionibus Orbium Coelestium, on the revolutions of the celestial spheres, published in 1543, the same year he died. And there's a story, probably embellished but too good not to mention, that a copy of the printed book was placed in his hands on his deathbed. Whether or not that's literally true, the timing is real. He held on to this work for decades before publishing it. He'd circulated a brief summary, called the Commentariolus, among friends as early as 1514, but the full book took nearly 30 more years to see print. Part of that delay was perfectionism. He kept refining his calculations. But part of it was almost certainly caution. Copernicus was a canon of the Catholic Church. He knew that claiming the Earth moved was theologically sensitive, even if the full storm over heliocentrism wouldn't break until decades after his death. And here's something that's important to understand about the Copernican model as he actually presented it. It wasn't as clean as you might expect. Copernicus still used circular orbits because circles were considered the perfect geometric form, and he couldn't quite bring himself to abandon that idea. The problem is that planetary orbits aren't actually circles. They're ellipses. And because Copernicus insisted on circles, he still needed some smaller epicycles of his own to make the math work. His model was simpler than Ptolemy's in its core idea, but in terms of raw predictive accuracy, it wasn't dramatically better. It was a philosophical revolution more than a practical one, at least at first. So the Copernican model sat there for a while, admired by some, ignored by others, and actively opposed by a few. The real fireworks came with the next generation, and the person who lit the fuse was a Danish nobleman with a metal nose and an obsession with precision. Tycho Brahe is one of the most colorful characters in the entire history of science. Born in 1546 to a wealthy Danish family, he lost part of his nose in a sword duel in his 20s, reportedly over a mathematical dispute, which is the most astronomer thing imaginable, and wore a prosthetic made of brass or possibly gold and silver for the rest of his life. But what made Tycho truly extraordinary wasn't his nose. It was his eyes and his instruments, and his almost fanatical commitment to measuring the sky more accurately than anyone had ever done before. Tycho built an observatory called Uraniborg on the island of Fyn, between Denmark and Sweden, and for over 20 years he catalogued the positions of stars and planets with a precision that was unprecedented. This was before the telescope, remember? Tycho used enormous sighting instruments, quadrants, sextants, armillary spheres, some of them several meters across, built with exquisite craftsmanship. And with these tools, night after night, year after year, he accumulated the most detailed and accurate set of astronomical observations the world had ever seen. Now, Tycho himself didn't fully accept the Copernican model. He proposed his own compromise system where the sun orbited the Earth, but all the other planets orbited the sun. a kind of hybrid that preserved a stationary Earth while incorporating some of Copernicus's geometric insights. It's a footnote today, but it mattered at the time. What mattered far more, though, was the data. Tycho's observations were a treasure beyond price, and near the end of his life, he hired a young German mathematician to help him analyze them. That mathematician was Johannes Kepler. Kepler arrived in Prague in 1600 to work with Tycho, and the two had a complicated relationship. Tycho was protective of his data and doled it out sparingly, while Kepler was desperate to get his hands on all of it. When Tycho died unexpectedly in 1601, just a year and a half after Kepler joined him, Kepler inherited the observations, and what he did with them changed our understanding of planetary motion forever. Kepler focused especially on Mars, because Mars had the most noticeably eccentric orbit. It deviated from a perfect circle more than the other visible planets, and he tried everything to make Mars fit a circular orbit. He spent years on it. He'd calculate a predicted position, compare it to Tycho's observations, find a discrepancy of about 8 arc minutes, a tiny sliver of sky, about a quarter of the apparent width of the full moon, and start over. 8 arc minutes. Most astronomers of the era would have shrugged that off as observational error. But Kepler trusted Tycho's data. He knew those measurements were accurate to within about 2 arc minutes. So an 8 arc minute error meant the model was wrong, not the data. This is such a crucial moment. The willingness to trust the data over the theory, to let a tiny discrepancy drive you to rethink everything. That's the heart of science right there. After years of grinding calculation, Kepler finally abandoned circles altogether and tried a different shape, an ellipse. An ellipse is like a stretched circle with 2 focal points instead of one center, and when he placed the Sun at one focus of an elliptical orbit, Mars's positions snapped into alignment with Tycho's observations beautifully. The errors vanished. From this breakthrough, Kepler formulated what we now call his 3 laws of planetary motion. The first law says that planets move in ellipses with the Sun at one focus. The second law says that a line drawn from the Sun to a planet sweeps out equal areas in equal times, which means planets move faster when they're closer to the Sun and slower when they're farther away. Think about that. It's not uniform motion. It's not a planet cruising along at the same speed all the time. It speeds up as it falls inward and slows down as it swings outward, and there's a precise mathematical relationship governing exactly how much. The third law came later, published in 1619 in a book called Harmonices Mundi, and it connects the size of a planet's orbit to the time it takes to complete one trip around the Sun. Specifically, the square of a planet's orbital period is proportional to the cube of its average distance from the Sun. That sounds abstract, but what it means in practice is astonishing. If you know how long a planet takes to orbit the Sun, you can calculate how far away it is. Or, if you know the distance, you can calculate the period. One number gives you the other, through a simple, universal ratio that applies to every planet in the solar system. Kepler published these laws, and they were correct, and they were beautiful, and they described the motions of the planets with far greater accuracy than anything before. But Kepler himself couldn't fully explain why they were true. He had the description, the how, but not the mechanism, the why. Why ellipses? Why equal areas in equal times? What force was reaching out from the Sun and shaping these orbits? Kepler had inklings. He speculated about a kind of magnetic influence emanating from the Sun, pushing and pulling the planets. He was groping toward the right answer, but he didn't have the tools to reach it. Those tools would come from an unlikely source, a premature baby born on Christmas Day, 1642, in a small manor house in Lincolnshire, England. A child so tiny that his mother said he could have fit inside a quart mug. A boy who grew up quiet, solitary, and intensely focused, who would become arguably the most important scientist who ever lived. And the thing he figured out, sitting in that quiet study at Cambridge, would finally answer Kepler's question. It would explain not just how the planets move, but why. Isaac Newton. You've heard the name 1,000 times, but it's worth pausing to appreciate just how strange and singular this person was. He was born prematurely, fatherless. His father had died 3 months before he arrived. His mother remarried when he was 3 and essentially left him with his grandmother. By most accounts, Newton's childhood was lonely and marked by a simmering anger he carried for years. He made lists of his sins as a young man, and among them, he included threatening to burn down his mother and stepfather's house. Not exactly the serene genius of legend, but he was ferociously intelligent, and when he arrived at Trinity College, Cambridge, in 1661, he devoured everything: Euclid, Descartes, the latest work in optics and mathematics. He was not a social creature. He barely ate, sometimes forgot to sleep, and had very few close relationships in his entire life. He was, in many ways, a mind that happened to inhabit a body, and the body was mostly an inconvenience. Now, here's where the famous story comes in, and I want to be careful with it, because it's been mythologized to the point of parody. The apple. You know the story. Newton sees an apple fall, and suddenly he understands gravity. The truth is more nuanced, but there is a real kernel to it. Newton himself told the story late in life to multiple people, including his friend William Stukeley, who recorded it. In 1666, Newton was back home at Woolsthorpe Manor because Cambridge had closed due to the plague, the Great Plague that swept through England. He was 23 years old, sitting in the garden, and he watched an apple fall. And the question that occurred to him wasn't why the apple fell. Everyone knew things fell. The question was how far that force extended. If the Earth's pull could reach the top of a tree, could it reach the top of a mountain? Could it reach the moon? Think about what a radical question that is. For thousands of years, the heavens and the earth were considered fundamentally different realms. Aristotle had said so explicitly. Terrestrial physics and celestial physics were separate, domains with separate rules. Things on earth fell because they sought their natural place. Things in the sky moved in circles because that was the nature of celestial matter. Newton looked at that apple and essentially asked, what if it's all the same? What if the force that pulls the apple to the ground is the exact same force that keeps the moon in its orbit? That insight, the unification of terrestrial and celestial mechanics, is arguably the single most important idea in the history of physics. But having the insight and proving it mathematically were two very different things. Newton needed to show that a force pulling the moon toward the Earth, combined with the moon's own sideways motion, would produce exactly the orbit we observe. And to do that, he needed to invent entirely new mathematics. He needed calculus. And so, during that plague year and the months surrounding it, Newton essentially invented calculus, worked out the foundations of his theory of gravity, and conducted groundbreaking experiments on the nature of light and color, all before he turned 26. It's one of the most extraordinary bursts of intellectual productivity in human history, and it happened in a farmhouse in rural England because a pandemic had sent a young man home from university. But here's the thing. Newton didn't publish any of this for years, decades in some cases. He was intensely private, almost pathologically afraid of criticism, and he sat on his discoveries like a dragon sitting on gold. It wasn't until 1687, more than 20 years after those initial insights, that he finally published the Principia Mathematica, and even then, it took the persistent prodding of Edmund Halley, yes, the comet guy, to get him to do it. Halley actually paid for the publication out of his own pocket, because the Royal Society had blown its budget publishing a book about fish. So what did the Principia actually say? Let's slow down here, because this is the moment everything changes. Newton laid out 3 laws of motion. You probably remember these from school. First, an object at rest stays at rest, and an object in motion stays in motion, unless acted on by an external force. Second, force equals mass times acceleration. Third, every action has an equal and opposite reaction. These 3 laws, combined with his law of universal gravitation, explained essentially all of mechanics. And the law of gravitation itself is breathtakingly simple. Every object in the universe attracts every other object with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. That's it. That's the whole law. You can write it in a single line of mathematics. And here's what's so beautiful about it. This one law, this inverse square relationship, explains Kepler's laws. All 3 of them. Newton showed mathematically that if gravity follows an inverse square law, then orbits must be conic sections, ellipses, parabolas, or hyperbolas, depending on the object's energy. For planets bound to the Sun, the orbits are ellipses, exactly as Kepler described. The equal area law? It falls directly out of the conservation of angular momentum under a central force. The third law, relating period to distance? Newton derived it as a straightforward consequence of the gravitational force between the Sun and a planet. Kepler had discovered the patterns. Newton explained the mechanism that produced them, the why behind the how. And it wasn't just planets. Suddenly, the same law explained why the moon orbits the Earth, why the tides rise and fall, why comets sweep through the inner solar system on long elliptical paths. Halley used Newton's methods to calculate the orbit of a bright comet he'd observed in 1682 and predicted it would return roughly every 76 years. He didn't live to see it. He died in 1742. But when the comet returned on Christmas Day, 1758, right on schedule, it was the most spectacular confirmation of Newtonian gravity anyone could have asked for. They named it Halley's Comet, and it's been returning like clockwork ever since. The last time it visited was 1986. The next time will be 2061. If you're listening to this and you're young enough, you might see it. Now, I want you to appreciate something about the solar system that Newton's work made clear for the first time. It's not just the sun pulling on the planets. Every object pulls on every other object. Jupiter pulls on Saturn. Saturn pulls on Jupiter. The Earth pulls on Mars, and Mars pulls back. The moon pulls on the Earth. That's what causes the tides, and the Earth pulls on the moon. It's a vast, interconnected web of gravitational interactions, and working out the precise motion of any one body means accounting for the pulls of everything else. This is what's called the n-body problem. And here's the humbling truth. For anything more than 2 bodies, there is no general exact solution. Newton himself recognized this. You can solve the 2-body problem perfectly. One planet orbiting one star, and you get a clean ellipse. But add a 3rd body, and the mathematics becomes ferociously complicated. In most cases, you have to approximate, iterate, calculate step by step. This might sound like a limitation, but it actually led to one of the most dramatic discoveries in the history of astronomy. By the late 1700s, astronomers had catalogued the planets out to Uranus, which William Herschel had discovered in 1781 using a homemade telescope from his garden in Bath, England. Herschel, by the way, was a musician by profession, an oboist and organist who had emigrated from Hanover. He built his own telescopes as a hobby, grinding mirrors by hand for hours at a stretch, while his sister Caroline read novels aloud to keep him from getting bored. And one night, scanning the sky methodically, he spotted something that wasn't a star. It moved. It was Uranus, the first planet discovered in recorded history that wasn't visible to the naked eye, the first one that the ancients hadn't known about. The solar system had suddenly gotten bigger, but as astronomers tracked Uranus over the following decades, they noticed something troubling. Its orbit didn't quite match the predictions. Even after accounting for the gravitational tugs of Jupiter and Saturn, Uranus kept drifting slightly from where it should have been. Something was pulling on it, something they couldn't see. And in the 1840s, two mathematicians, John Couch Adams in England and Urbain Le Verrier in France, independently tackled the problem. They asked, if there's an unknown planet out beyond Uranus, where would it have to be to produce exactly the orbital deviations we're observing? Both men worked through the grueling calculations and arrived at nearly the same answer. Le Verrier sent his predicted position to the Berlin Observatory, and on September 23, 1846, the astronomer Johann Galle pointed his telescope at the coordinates and found Neptune within 1 degree of where Le Verrier said it would be. Within 1 degree, on the very first night he looked. Think about what that means. A planet was discovered not by looking through a telescope, but by doing mathematics. The gravitational theory that Newton had laid out a century and a half earlier was so precise, so reliable, that you could use it to predict the existence of a world no human eye had ever seen. That's the power of understanding the mechanism, not just the pattern. Kepler could tell you where Mars would be next year. Newton could tell you why, and that why was powerful enough to reveal hidden planets. And this success made the next puzzle all the more maddening. Because there was one orbit in the solar system that Newton's gravity couldn't quite explain, and it belonged to the planet closest to the Sun. Mercury. The innermost planet traces an ellipse around the Sun, like all the planets, but that ellipse itself slowly rotates. The point of closest approach, called the perihelion, shifts a tiny bit with each orbit. Most of this precession is caused by the gravitational pulls of the other planets, and Newtonian mechanics accounts for almost all of it. Almost. But there's a leftover, about 43 arcseconds per century that couldn't be explained. 43 arcseconds is tiny. It's roughly the width of a dime seen from a mile away. But it was real, it was persistent, and it drove astronomers slightly crazy for decades. Le Verrier, riding high on his Neptune triumph, naturally proposed the same solution. There must be another unseen planet, this time orbiting inside Mercury's orbit, closer to the Sun. He even gave it a name, Vulcan, and for years, people searched for it. Some even claimed to have seen it transiting across the face of the Sun. But Vulcan didn't exist. The anomaly in Mercury's orbit wasn't caused by a hidden planet. It was caused by something far stranger, something that wouldn't be understood until 1915, when a German-born physicist working in Berlin published a new theory of gravity that would supersede Newton's, not by proving it wrong exactly, but by revealing it as a special case of something deeper. That physicist, of course, was Albert Einstein, And the theory was general relativity. And what Einstein showed about the nature of gravity, about the very fabric of space and time, well, it changes everything about how we understand not just Mercury's orbit, but the entire structure of the solar system, the bending of light near the sun, the way time itself runs differently depending on where you are in a gravitational field. It's one of those ideas that starts out sounding abstract and then turns out to be woven into technologies you use every single day, including the GPS satellite constellation orbiting above your head right now, which has to account for relativistic time dilation to give you accurate directions to the nearest coffee shop. But to really appreciate what Einstein did, we need to talk about what gravity actually is under general relativity. Because Newton told us what gravity does. He gave us the equation, the inverse square law, the beautiful mathematical machinery that lets you predict orbits and tides and trajectories. But Newton himself admitted he had no idea what gravity actually was. How does the sun reach across 93 million miles of empty space and pull on the Earth? What's the mechanism? Newton called this action at a distance, and it bothered him deeply. In a famous letter, he wrote that the idea of one body acting on another through a vacuum with nothing mediating the interaction was so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. He knew his theory worked. He just couldn't explain why it worked. And for over 2 centuries, nobody could. Einstein's answer is one of the most beautiful ideas in all of physics, and it starts with a deceptively simple observation. Imagine you're standing in an elevator, not a glass one, just a sealed box, and you feel your feet pressing against the floor. You feel weight. Now, here's Einstein's question. Can you tell, just from that sensation alone, whether the elevator is sitting still on the surface of the Earth, with gravity pulling you down, or whether the elevator is out in deep space, far from any planet, but accelerating upward at exactly 9.8 meters per second squared? The answer is no. You can't tell the difference. The feeling is identical. Your feet press against the floor with the same force. A ball you drop from your hand falls to the floor in exactly the same way. Every experiment you could perform inside that sealed box gives you the same result in both scenarios. Einstein called this the equivalence principle, the idea that gravitational acceleration and the acceleration of a reference frame are fundamentally indistinguishable. And that might sound like a minor observation, almost trivially obvious, but Einstein had this extraordinary ability to take something that seemed obvious and follow it relentlessly to its logical conclusion. And the conclusion he reached was staggering. If gravity and acceleration are truly equivalent, then gravity isn't a force at all, not in the way Newton imagined it. Instead, gravity is geometry. It's the curvature of space-time itself. Here's the analogy that usually helps. Imagine a stretched rubber sheet, pulled tight and flat. Now place a heavy bowling ball in the center. The sheet deforms. It curves downward around the ball, creating a kind of well, a depression. Now roll a marble across the sheet. If you roll it in a straight line far from the bowling ball, it travels pretty much straight. But if you roll it near the bowling ball, it curves. It follows the contour of the deformed sheet. It might even spiral inward. And here's the key insight. The marble isn't being pulled by the bowling ball. There's no force reaching out and tugging on it. The marble is simply following the straightest possible path through curved space. It thinks it's going straight. The space itself is bent. That's what Einstein proposed the sun does to the space around it. The The sun's mass warps the fabric of space-time, and the Earth doesn't orbit because some invisible rope is pulling it inward. The Earth orbits because it's following the straightest possible path, what mathematicians call a geodesic, through the curved space-time created by the sun's mass. It's rolling along the contours of a gravitational well, the same way that marble rolls around the depression in the rubber sheet. And this isn't just a metaphor. Einstein wrote down the precise mathematical equations, the field equations of general relativity, that describe exactly how mass and energy curve space-time, and how that curvature dictates the motion of everything within it. The math is ferocious. Tensor calculus, Riemannian geometry, stuff that makes even professional physicists sweat. But the core idea is breathtakingly elegant. Matter tells space-time how to curve. Space-time tells matter how to move. And here's where Mercury comes back into the story. Newton's gravity predicts that Mercury should orbit the Sun in a nearly perfect ellipse, with that ellipse precessing, rotating slowly, due to the gravitational tugs of Venus, Jupiter, and the other planets. And it does precess quite a lot, actually. But when you add up all the Newtonian contributions, you come up short by those stubborn 43 arcseconds per century. Einstein's equations, though, when applied to Mercury's orbit, naturally produce exactly that extra precession. Not approximately. Exactly. The reason is that Mercury orbits so close to the Sun, deeper in the Sun's gravitational well than any other planet, where the curvature of space-time is most pronounced. Newtonian gravity, which treats space as flat and gravity as an instantaneous force, misses the subtle effects of that curvature. General relativity captures them perfectly. When Einstein completed this calculation in November 1915, he was reportedly so excited he had heart palpitations. He later told a colleague it was the most thrilling moment of his scientific life. And you can understand why. For decades, Mercury's orbit had been this nagging, unexplained anomaly, a tiny crack in the edifice of Newtonian physics. And Einstein's brand new theory, derived from pure thought about elevators and falling objects and the geometry of space-time, filled that crack perfectly, without any fudge factors, without any free parameters to adjust. It just worked. But Einstein knew that explaining an existing anomaly wasn't enough. A truly great theory needs to make predictions, tell you something you didn't already know, something you can go out and test. And general relativity made a dramatic one. If massive objects curve space-time, then light itself, traveling through that curved space-time, should follow curved paths. A beam of starlight passing close to the Sun should be deflected, bent slightly inward by the Sun's gravitational well. Newton's theory actually predicts a small deflection too, if you treat light as particles with some effective mass, but Einstein's prediction was exactly twice as large. So there was a clear, testable difference between the two theories. The test came in 1919 during a total solar eclipse. You need an eclipse because normally the Sun is so blindingly bright that you can't see stars near it. But during totality, when the Moon blocks the Sun's disk, you can photograph the stars that appear close to the Sun's edge and measure whether their apparent positions have shifted compared to where they are when the Sun isn't nearby. The British astronomer Arthur Eddington organized 2 expeditions, one to the island of Principe off the west coast of Africa, and another to Sobral in northern Brazil. The weather was terrible at Principe, clouds rolling in right as totality began, but Eddington managed to get a few usable photographs. And when the measurements were analyzed, the deflection of starlight matched Einstein's prediction, not Newton's. The announcement made Einstein a global celebrity almost overnight. Newspapers around the world ran headlines about the theory that had overthrown Newton, which is a bit dramatic. Newton's theory still works beautifully for nearly everything in everyday life and most of the solar system. But in the strong gravitational fields near the sun, or at the precision required by modern technology, you need Einstein. And that brings us to something wonderfully practical. Those GPS satellites we mentioned, there are about 31 of them orbiting Earth at an altitude of roughly 20,000 kilometers. Each one carries an atomic clock, and the whole system works by measuring the tiny differences in the time it takes signals from multiple satellites to reach your phone. Your phone uses those time differences to triangulate your position. But here's the thing. Time runs at different rates depending on your position in a gravitational field. This is not science fiction. This is measured, confirmed, engineering critical fact. A clock in orbit, farther from Earth's mass, in weaker gravity, ticks slightly faster than a clock on the ground. The difference is tiny, about 45 microseconds per day gained due to the gravitational effect. There's also a smaller opposing effect from the satellite's orbital velocity, which slows the clock down by about 7 microseconds per day due to special relativity. The net result is that the satellite clocks gain roughly 38 microseconds per day compared to ground clocks. If you didn't correct for this, the position errors would accumulate at about 10 kilometers per day. Your GPS would be useless within hours. So every GPS satellite has its clock rate deliberately adjusted before launch to account for relativistic effects. Einstein's 1915 theory of curved spacetime is literally baked into the firmware of satellites that help you navigate to the grocery store. Think about that for a second. A theory born from thought experiments about elevators and falling objects, developed to explain 43 arc-seconds of orbital drift per century on a planet no human has ever visited, turns out to be essential for a navigation system used by billions of people every day. That's the thing about fundamental physics. You never know where it's going to matter. So by the early 20th century, our understanding of the solar system had undergone this extraordinary transformation. We'd gone from Ptolemy's crystalline spheres to Copernicus's sun-centered rearrangement to Kepler's ellipses to Newton's universal gravitation to Einstein's curved spacetime. Each step didn't so much destroy what came before as deepen it, reveal it as a special case of something richer. And each step was driven by paying attention to small discrepancies, the things that didn't quite fit. Retrograde motion, the orbit of Mars, 43 arc-seconds per century. But here's what's interesting. While all of this theoretical work was transforming our understanding of how the solar system works, the laws governing its motion, there was a parallel revolution happening in our understanding of what the solar system actually is. What are these planets made of? How did they form? Why is the solar system arranged the way it is, with small rocky worlds close to the sun and gas giants farther out? Why do most planets orbit in roughly the same plane, in the same direction? These are different kinds of questions, not about the laws of motion, but about origins and composition and structure. And answering them required entirely different tools. The first serious attempt to explain how the solar system formed came from an unlikely source. In 1755, a young German philosopher named Immanuel Kant, yes, that Kant, the one you might know from philosophy classes, published a book called Universal Natural History and Theory of the Heavens. Kant proposed that the solar system had condensed from a vast rotating cloud of gas and dust. The cloud collapsed under its own gravity, spun faster as it contracted, flattened into a disk, and the planets coalesced from material within that disk. It was remarkably prescient. A few decades later, the French mathematician Pierre-Simon Laplace independently developed a similar idea with more mathematical rigor, and the concept became known as the nebular hypothesis. And in broad strokes, it's still the foundation of how we understand solar system formation today, though the details have been revised dramatically. But to really test these ideas, you needed to know what the sun and planets were actually made of. And for most of human history, that seemed like an impossible question. In 1835, the French philosopher Auguste Comte famously declared that the chemical composition of the stars was something humanity could never know, the one piece of knowledge forever beyond our reach. It's one of the most spectacularly wrong predictions in the history of science, because even as Comte was writing those words, the tool that would prove him wrong was already being developed. It involved something as simple as passing sunlight through a glass prism and looking very, very carefully at what came out the other side. And what came out wasn't just a smooth rainbow. That's the key. You'd expect a perfect, unbroken band of color, red bleeding into orange, into yellow, into green, into blue, into violet. And from a distance, that's more or less what you see. But when you look closely, really closely, there are dark lines, thin, sharp gaps in the spectrum where specific colors are simply missing. Little slivers of darkness scattered across the rainbow like someone had drawn on it with the finest possible pen. The first person to really document these lines was a Bavarian optician named Joseph von Fraunhofer, and his story is one of those improbable tales that history seems to specialize in. Fraunhofer was born in 1787, orphaned at 11, and apprenticed to a glassmaker in Munich. A brutal apprenticeship, by all accounts. When he was 14, the workshop building collapsed on top of him, and he was trapped in the rubble. The rescue effort drew the attention of no less than the Prince Elector of Bavaria, who took an interest in the boy and gave him money and books. That patronage changed everything. Fraunhofer used it to educate himself in optics and eventually became one of the finest lens makers in Europe. And in 1814, while testing the quality of his glass prisms, he turned a small telescope toward the sun's spectrum and noticed those dark lines. Hundreds of them. He carefully mapped 574 of them and labeled the most prominent ones with letters A, B, C, D, and so on. Some of those letter designations are still used today, 2 centuries later. The pair of dark lines he labeled D, for instance, sitting right in the yellow part of the spectrum. Those turn out to be enormously important, and we'll come back to them in just a moment. Now, Fraunhofer didn't fully understand what caused these lines. He noticed that some of them matched the positions of bright lines he saw when he looked at flames and artificial light sources, which was a tantalizing clue, but the complete explanation had to wait about 45 years. And it came from 2 men working together in Heidelberg, the physicist Gustav Kirchhoff and the chemist Robert Bunsen. Yes, that Bunsen, the one the burner is named after. The Bunsen burner wasn't just a convenient lab tool. It was actually designed specifically for this work, because Bunsen needed a flame that burned clean and colorless without adding its own light to the experiment. Here's what Kirchhoff and Bunsen figured out, starting around 1859. Every chemical element, when heated until it glows, emits light at very specific wavelengths, specific colors, if you like. Sodium, for instance, produces a bright, distinctive yellow-orange glow. You've seen it. Those old-fashioned orange streetlights? That's sodium vapor, and that particular shade of orange comes from sodium atoms emitting light at 2 very precise wavelengths, right around 589 nanometers. And here's the beautiful part. Those 2 wavelengths correspond exactly to Fraunhofer's D lines. Exactly. What Kirchhoff realized was that this works in reverse too. If you shine a continuous spectrum of white light through a cooler gas of sodium atoms, those atoms will absorb light at precisely the same wavelengths they would emit if they were hot. So instead of bright lines, you get dark lines, gaps in the spectrum, absorption lines, and that's what the Fraunhofer lines in the solar spectrum are. The sun's core produces a continuous spectrum, a smooth rainbow of every wavelength. But as that light passes outward through the cooler gases in the sun's atmosphere, atoms of various elements absorb their signature wavelengths. Each element leaves its own fingerprint, its own unique pattern of dark lines. Iron leaves one pattern. Hydrogen leaves another. Calcium, magnesium, sodium. Each one has a barcode as distinctive as a fingerprint. Think about what that means. You don't need to visit the sun. You don't need to scoop up a sample. You just need to catch its light, spread it into a spectrum, and read the barcode. Comte said we could never know the composition of the stars, and here was a method that could tell you exactly which elements were present in a star billions of miles away just from analyzing its light. It's one of the most powerful tools in all of science, and it's fundamentally simple. It's just light and glass and careful observation, and it delivered surprises almost immediately. In 1868, during a solar eclipse, the French astronomer Jules Janssen and the English astronomer Joseph Norman Lockyer independently observed a bright spectral line in the sun's chromosphere that didn't match any known element on Earth. Lockyer proposed that it belonged to a new element, one that existed on the sun but hadn't yet been found here. He named it helium, from the Greek word helios, for sun. It wasn't isolated on Earth until 1895, almost 3 decades later, an element discovered on the sun before it was found on our own planet. That's spectroscopy for you. So by the late 19th century, scientists had an extraordinary new capability. They could determine the chemical composition of the sun, and in principle, of any star or glowing object they could point a telescope at. And when they turned this tool on the planets, things got even more interesting, though also more complicated, because planets don't generate their own visible light the way stars do. They shine by reflecting sunlight. So the spectrum you get from a planet is the sun's spectrum, modified. The sunlight passes through the planet's atmosphere on the way in and on the way out, and whatever gases are in that atmosphere leave their own absorption signatures on top of the solar ones. It takes careful work to tease apart which lines come from the sun and which come from the planet. But it can be done. Now, let's pull back for a moment and think about where we are in the story. We've got Newton's gravity telling us how things move. We've got Einstein's refinement telling us why space-time curves. We've got spectroscopy telling us what things are made of. And we've got Kant and Laplace's nebular hypothesis giving us a rough framework for how the whole system formed. By the early 20th century, these threads were starting to weave together into something much more complete. But there were still enormous gaps, and filling them required actually going out there, or at least sending something out there. The space age changed everything, and I mean everything. Before spacecraft, our knowledge of the planets was built almost entirely from what we could see through telescopes and deduce from spectra. We knew Mars had polar caps and seasonal changes in surface color. We knew Jupiter had bands and a great red spot. We knew Saturn had rings. But the details were fuzzy, sometimes literally. Venus, for instance, was completely shrouded in clouds, and serious scientists in the 1950s still debated whether its surface might be covered in swamps or oceans. Some thought it could be habitable. The truth, when Venera and Mariner spacecraft finally got there, was far more dramatic and far less hospitable. The Soviet Venera program is one of the great underappreciated sagas of space exploration. Starting in the early 1960s, the Soviets launched mission after mission toward Venus, and most of them failed. Lost during launch, lost in transit, crushed by the atmosphere before reaching the surface. Venus's atmosphere is about 90 times denser than Earth's. 90 times. The surface pressure is equivalent to being nearly a kilometer underwater in Earth's oceans, and the temperature at the surface is around 465 degrees Celsius, hot enough to melt lead. The atmosphere is almost entirely carbon dioxide, with clouds of sulfuric acid. It is, by any reasonable standard, hellish. And the Venera engineers had to design spacecraft that could survive long enough to take measurements and send them back. Venera 7, in 1970, became the first spacecraft to successfully transmit data from the surface of another planet. It lasted about 23 minutes before succumbing to the conditions. Later, Venera missions managed to take actual photographs of the surface. Rocky, flat, dimly lit by the thick atmosphere overhead, like a permanent overcast day at oven temperatures. Those images are haunting. They show a world that might have looked something like Earth billions of years ago, but took a catastrophically different path. And that's a theme that runs through everything we've learned from planetary exploration. The solar system is a set of natural experiments. You have roughly similar starting materials, roughly similar processes, but different initial conditions, different distances from the sun, different masses, different compositions, and you end up with wildly different outcomes. Venus and Earth are almost the same size, almost the same mass, made of roughly the same stuff. They're sometimes called sister planets, but one has oceans and life and a nitrogen-oxygen atmosphere, and the other has a runaway greenhouse effect and surface conditions that destroy spacecraft in minutes. Understanding why they diverged is one of the deepest questions in planetary science, and it connects directly back to that nebular hypothesis. Because the answer has to do with where each planet formed, how much water it started with, how its atmosphere evolved, and whether certain feedback loops tipped one way or the other. Mars tells a different version of the same story. Smaller than Earth, farther from the sun, with a thin atmosphere that's also mostly carbon dioxide, but at less than 1% of Earth's surface pressure. Mars today is cold and dry and apparently lifeless, at least on the surface. But the evidence from orbiters and rovers, Spirit, Opportunity, Curiosity, Perseverance, has painted a picture of a planet that was once warmer and wetter. There are ancient river channels carved into the surface, mineral deposits that only form in the presence of liquid water, lake beds, and what appear to be ancient shorelines. Mars had a thicker atmosphere once. It had flowing water. Something changed. The leading explanation involves Mars's lack of a global magnetic field. Earth's magnetic field, generated by convection currents in its liquid iron outer core, shields our atmosphere from the solar wind, that constant stream of charged particles flowing outward from the sun. Mars, being smaller, cooled faster, its core solidified or at least stopped generating a strong dynamo, and without that magnetic shield, the solar wind gradually stripped away its atmosphere over hundreds of millions of years. As the atmosphere thinned, the surface pressure dropped, liquid water became unstable, and Mars dried out. It's a slow-motion catastrophe playing out over geological time, and we can read the evidence of it in the rocks and minerals that rovers are examining right now, on the surface, as you lie here listening to this. The outer solar system is a completely different regime. Once you get past Mars, past the asteroid belt, that loose collection of rocky bodies orbiting between Mars and Jupiter, remnants of a planet that never formed because Jupiter's gravity kept stirring things up. You enter the realm of the gas giants and ice giants, and the rules change. Jupiter and Saturn are enormous. Jupiter alone contains more mass than all the other planets combined, about 318 times Earth's mass. It's mostly hydrogen and helium, the same stuff the Sun is made of. And in fact, if Jupiter had been maybe 70 or 80 times more massive, it would have had enough pressure and temperature at its core to ignite hydrogen fusion and become a star. A small, dim red dwarf star, but a star nonetheless. We'd be living in a binary star system. Think about that for a second. The difference between a planet and a star is, in some sense, just a matter of degree, just mass. Jupiter's internal structure is something we're still working out, but the current picture is remarkable. The outer layers are gaseous hydrogen and helium. That's what we see, those beautiful swirling bands and storms. But as you go deeper, the pressure increases relentlessly. At a certain depth, the hydrogen is compressed so intensely that it transitions into a state called metallic hydrogen, a form of hydrogen so dense that electrons are squeezed free of their atoms and can flow like they do in a metal. It conducts electricity. And that's significant because electric currents in metallic hydrogen, driven by Jupiter's rapid rotation, Jupiter spins once every 10 hours, despite being 11 times Earth's diameter, generate Jupiter's enormous magnetic field, the strongest of any planet in the solar system. That magnetic field traps charged particles in radiation belts so intense that they'd be lethal to an unshielded human in minutes. The Juno spacecraft, orbiting Jupiter right now, carries its sensitive electronics inside a titanium radiation vault to survive the environment. And then there are Jupiter's moons, and this is where things get really fascinating. Because Jupiter isn't just a planet. It's almost like a miniature solar system unto itself. Jupiter has at least 95 known moons, but 4 of them are in a class entirely by themselves. These are the Galilean moons, Io, Europa, Ganymede, and Callisto, named for Galileo, who spotted them through his telescope back in 1610 and realized they were orbiting Jupiter, not Earth, not the Sun, but Jupiter. That observation, as we talked about earlier, was one of the nails in the coffin of the geocentric model. But what's really captivating about these 4 moons isn't their historical significance. It's what we've learned about them since. Let's start with Io, the innermost of the 4. Io is the most volcanically active body in the entire solar system. Not one of the most active, period. When Voyager 1 flew past in 1979, navigation engineer Linda Morabito was processing images to refine the spacecraft's trajectory and noticed a strange plume rising off the limb of Io. It was a volcanic eruption, caught in the act, a fountain of sulfur and sulfur dioxide shooting hundreds of kilometers above the surface. That was the first time anyone had observed active volcanism on another world. And Io isn't just occasionally volcanic. Its entire surface is being continuously resurfaced by lava flows and eruptions. There are no impact craters on Io because they get buried almost as fast as they form. The surface is this wild patchwork of yellows and oranges and blacks, sulfur compounds, and silicate lavas. So why is Io so volcanically active? It's not because of radioactive decay in its interior, like what drives most of Earth's internal heat. It's tidal heating. Io orbits close to Jupiter, and Jupiter's gravity is immense. But here's the key. Io doesn't orbit in isolation. Europa and Ganymede are out there too, and the three moons are locked in what's called a Laplace resonance. For every one orbit Ganymede completes, Europa completes exactly 2, and Io completes exactly 4. This gravitational relationship means Io's orbit is kept slightly elliptical. It's not a perfect circle. And because the orbit is elliptical, the tidal forces from Jupiter vary as Io moves closer and farther away. Jupiter's gravity literally flexes Io, squeezing and stretching it, and that mechanical flexing generates heat, enormous amounts of heat deep in Io's interior, enough to melt rock, enough to drive hundreds of active volcanoes simultaneously. Now, hold that idea of tidal heating in your mind, because it's about to become even more important. Move one moon outward and you reach Europa. Europa is smaller than our moon, and at first glance, it looks like a smooth, icy cue ball. Its surface is water ice, and it's one of the smoothest surfaces in the solar system. Very few large craters, very few mountains. But look closer, and you see something extraordinary. The surface is crisscrossed with an intricate network of reddish-brown lines, cracks, and ridges. Some of these features look like ice flows that have broken apart and refrozen, like pack ice in the Arctic Ocean. And the relative scarcity of impact craters tells you something profound. This surface is young, geologically young. Something is erasing craters, resurfacing Europa, and the best explanation is that beneath that ice shell, there's a global ocean of liquid water. Think about what that means. Liquid water. Not in the past, not maybe, not a little bit. A global ocean, possibly 60 to 100 miles deep, containing perhaps 2 to 3 times the volume of all Earth's oceans combined. And it's kept liquid by the same mechanism that tortures Io, tidal heating. Europa is farther from Jupiter, so the heating is less intense, but it's enough to maintain liquid water beneath an ice crust that might be 10 to 30 kilometers thick. And this is where the conversation shifts from geology to something almost philosophical. When we talk about the search for life beyond Earth, Europa is one of the most compelling places in the entire solar system. You have liquid water, you likely have a rocky seafloor where that water meets silicate rock, and you have energy. Tidal heating could drive hydrothermal vents on that seafloor, similar to the deep sea vents on Earth, where entire ecosystems thrive without any sunlight at all, powered purely by chemical energy. Life on Earth may have originated at such vents. So Europa has the 3 ingredients astrobiologists care about most: liquid water, chemistry, and energy. NASA is sending a spacecraft called Europa Clipper. It launched in October 2024 to perform dozens of close flybys, studying the ice shell, measuring the ocean's salinity, looking for plumes of water vapor that might be venting through cracks in the ice. If water is escaping into space, you could potentially fly through it and taste the ocean without ever having to drill through the ice. Ganymede, the next moon out, is the largest moon in the solar system, bigger than Mercury, actually. It has its own magnetic field, the only moon known to have one, which tells you it has a partially molten iron core. And Callisto, the outermost Galilean moon, is this ancient, heavily cratered world that seems to have been geologically dead for billions of years. It's a time capsule. The contrast between the 4 Galilean moons, from the volcanic fury of Io to the frozen stillness of Callisto, is a beautiful illustration of how orbital position and tidal interactions can produce radically different worlds from similar starting materials. Let's keep moving outward. Saturn. If Jupiter is the solar system's heavyweight, Saturn is its showpiece. Those rings are simply one of the most visually stunning things in nature, and they're also one of the most instructive. Saturn's rings are made almost entirely of water ice, particles ranging from tiny grains to chunks the size of houses, all orbiting Saturn in an incredibly thin, flat disk. The rings span about 280,000 kilometers from edge to edge, but they're typically only about 10 meters thick. If you scaled Saturn's rings down to the diameter of a football field, they'd be thinner than a razor blade. That flatness isn't accidental. It's physics. Any particle in the ring system that has an orbit tilted above or below the plane will eventually collide with other particles, and those collisions cancel out the vertical component of motion while preserving the horizontal orbital motion. Over time, everything settles into a thin disk. It's the same reason the solar system itself is roughly flat, the same reason spiral galaxies are flat. It's a universal consequence of angular momentum conservation and collisional dissipation. Here's something surprising, though. Saturn's rings are probably young, cosmically young. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, measured the mass of the rings and found them to be less massive than expected. They're also remarkably bright and clean, mostly pure water ice without much contamination from the dark, dusty debris that constantly drifts through the outer solar system. If the rings were billions of years old, they should have accumulated more gunk. The current thinking is that Saturn's rings might be only 100 to 400 million years old. That means they might have formed during the age of dinosaurs on Earth. Something happened. Maybe a moon wandered too close and was torn apart by tidal forces, or maybe a comet impact shattered a moon, and the debris settled into the ring system we see today. Saturn might not always have had its rings, and it might not keep them forever. They're slowly raining down onto the planet, and estimates suggest they could be gone in another 100 million years or so. We're lucky to be alive during the window when Saturn has rings. Saturn also has its own collection of remarkable moons. Titan is the big one. It's the second largest moon in the solar system, bigger than Mercury, and the only moon with a thick atmosphere. Titan's atmosphere is mostly nitrogen, like Earth's, but it's about 1.5 times denser than ours at surface level. And the surface of Titan has lakes and seas and rain, but not water. It's far too cold for liquid water on the surface, about minus 179 degrees Celsius. The liquid on Titan is methane and ethane, hydrocarbons. Methane plays the role on Titan that water plays on Earth. It evaporates, forms clouds, falls as rain, collects in lakes and rivers, and carves channels in the landscape. The Huygens probe, which the Cassini mission carried to Saturn and released in January 2005, descended through Titan's thick orange haze and landed on the surface, the most distant landing ever achieved by a spacecraft. The images it sent back showed rounded pebbles of water ice, smoothed by flowing liquid, sitting on a damp surface. It looked eerily like a riverbed on Earth, except everything was made of the wrong materials. And then there's Enceladus, a tiny moon only about 500 kilometers across. You could fit it inside the state of Arizona. Enceladus should be a frozen, dead little ice ball. But in 2005, Cassini flew past and discovered something astonishing. Geysers of water vapor and ice particles erupting from long fractures near the South Pole, features nicknamed tiger stripes. These plumes shoot material hundreds of kilometers into space, and some of that material feeds Saturn's E-ring, the faint outermost ring. Cassini flew through those plumes multiple times and analyzed the composition. It found water, salt, silica nanoparticles, and, here's the kicker, molecular hydrogen. The silica nanoparticles suggest hot water interacting with rock at temperatures above about 90 degrees Celsius, which points to hydrothermal activity on the seafloor. The molecular hydrogen could be a chemical energy source for microbial life. So Enceladus, this tiny moon that nobody was paying much attention to before Cassini, turns out to have a subsurface ocean with hydrothermal vents and potential chemical energy for life. It's another Europa situation, but in some ways even more tantalizing because the ocean is venting directly into space. You don't have to drill through anything to sample it. Beyond Saturn, the solar system becomes a colder, lonelier place. Uranus and Neptune are the ice giants, a different category from the gas giants. They're smaller than Jupiter and Saturn, and while they have hydrogen and helium atmospheres, their bulk composition is dominated by heavier volatile compounds, water, ammonia, and methane ices, hence the name. Uranus is famous for its extreme axial tilt. It's tipped over almost 98 degrees, essentially rolling around the sun on its side. Something hit it, hard, early in solar system history. A protoplanet, maybe 1 to 3 times Earth's mass, probably slammed into Uranus and knocked it sideways. That collision may also explain why Uranus radiates almost no internal heat, unlike every other giant planet. The impact might have mixed its interior in a way that allowed the primordial heat to escape early, or it might have created a thermal barrier that traps heat deep inside. We honestly aren't sure. Uranus has been visited by exactly one spacecraft, Voyager 2, in January 1986, and we got a brief flyby's worth of data. There are serious proposals for a dedicated Uranus orbiter mission because the ice giants are the least understood class of planet in our solar system, and yet they might be the most common type of planet in the galaxy. Exoplanet surveys suggest that ice giant-sized worlds are extremely abundant around other stars. Understanding Uranus and Neptune might be the key to understanding the most typical planets in the universe. Neptune, the outermost planet, is a deep, vivid blue. Methane in its atmosphere absorbs red light and reflects blue. When Voyager 2 arrived in August 1989, it found something nobody expected: the strongest winds measured on any planet, howling at speeds up to 2,100 kilometers per hour. That's puzzling, because Neptune is so far from the sun that it receives very little solar energy to drive weather systems. The winds must be powered largely by Neptune's internal heat. Neptune radiates about 2.6 times as much energy as it receives from the sun. Where that internal heat comes from, billions of years after formation, is still being studied. And Neptune has Triton, one of the strangest moons in the solar system. Triton orbits Neptune backward, retrograde, which almost certainly means it wasn't born alongside Neptune. It was captured. Triton is probably a Kuiper belt object, a world from the outer reaches of the solar system that Neptune's gravity snagged and pulled into orbit. And that capture would have been catastrophic for Neptune's original moon system. The gravitational disruption of inserting a large retrograde body would have scattered or destroyed whatever moons were there before. Triton itself has a surface of nitrogen ice, and Voyager 2 spotted active geysers, plumes of nitrogen gas and dark dust shooting up through the ice. Even out here, nearly 4.5 billion kilometers from the sun, there's geological activity. Beyond Neptune, we enter the realm of the Kuiper belt and the scattered disk, a vast population of icy bodies orbiting in the cold outer reaches. Pluto lives here, of course, reclassified from planet to dwarf planet in 2006. And when New Horizons flew past in July 2015, it revealed a world of breathtaking complexity. Nitrogen glaciers flowing across the surface, a heart-shaped plain of frozen nitrogen ice that appears to be convecting, slowly overturning like a lava lamp, mountains of water ice standing kilometers high, and a thin, haze-layered atmosphere. Nobody expected Pluto to be so geologically active, so varied, so alive in its own quiet way. And Pluto is just one member of a vast population. Eris, Makemake, Haumea, Sedna. There are thousands of known objects out here, and probably millions more waiting to be found. Some of them have orbits that take them far, far from the Sun. Sedna, for example, swings out to nearly 900 astronomical units at its most distant point, taking about 11,000 years to complete one orbit. What shaped these extreme orbits is still debated, and some researchers have suggested that a distant, undiscovered planet, sometimes called Planet 9, might be gravitationally sculpting the orbits of these far-flung objects. The evidence is circumstantial and contested, but the search continues. And here's what's beautiful about all of this. From the volcanic fury of Io to the nitrogen glaciers of Pluto, from Saturn's razor-thin rings to the subsurface oceans of Europa and Enceladus, every one of these worlds operates according to the same fundamental physics, the same gravity that Newton described, the same thermodynamics, the same chemistry. The diversity comes not from different laws, but from different initial conditions and different histories. A moon that orbits a little closer gets tidally heated into volcanic madness. One that orbits a little farther stays frozen and cratered for 4 billion years. A planet that forms with a little more mass becomes a gas giant. A little less, and it stays rocky. The solar system is like a laboratory where nature has run the same experiment under slightly different conditions over and over, and the results are spread out across billions of kilometers for us to study. And we've barely started. We've sent spacecraft to every planet, yes, but most of them were brief flybys, a few hours of close observation after years of travel. The detailed exploration, the kind where you orbit for years and send landers and drill through ice shells, that's still mostly ahead of us. Which brings us to something worth thinking about. How all of this holds together. How the solar system maintains its structure over billions of years, and what we've learned about its long-term stability. Because when you have 8 planets, hundreds of moons, millions of asteroids and comets, all orbiting under mutual gravitational influence, you might wonder whether the whole arrangement is actually stable, or whether it's slowly drifting toward some future catastrophe. And the answer to that question turns out to be surprisingly unsettling and also deeply fascinating. Because the honest answer, the one that took centuries of mathematics to arrive at, is that we don't fully know. And what we do know suggests the solar system is stable, but only just, only by a hair. And that hair might not hold forever. Let's start with why this question is so hard. You might think, well, Newton gave us the law of gravity, Kepler gave us the orbital shapes, we've got computers now. Just calculate everything forward a few billion years and see what happens. And in principle, yes, that's exactly what you do. But here's the thing. Newton's gravity works perfectly for 2 bodies, the Sun and 1 planet. You can solve that exactly. Beautiful elliptical orbits, repeating forever, case closed. But the moment you add a 3rd body, the Sun, Jupiter, and Saturn, say, the math becomes fundamentally different. Not just harder. Fundamentally unsolvable in the general case. This is the famous 3-body problem, and it's been tormenting physicists and mathematicians since Newton himself recognized it. Newton actually worried about this. He noticed that Jupiter and Saturn seemed to be tugging on each other in ways that might, over long periods, destabilize their orbits. and he essentially threw up his hands and suggested that God might occasionally intervene to reset things, which is a remarkable statement from the man who gave us deterministic physics. Even he couldn't see a way to guarantee long-term stability through math alone. The next person to really wrestle with this was Pierre-Simon Laplace, who we've already met with his nebular hypothesis. In the late 1700s, Laplace tackled the Jupiter-Saturn problem head-on. He discovered something beautiful, that the apparent drift in their orbits wasn't a one-way slide toward chaos, but actually a very long oscillation. Jupiter and Saturn are locked in what's close to a 5-to-2 orbital resonance. Jupiter goes around roughly 5 times for every 2 orbits of Saturn. And this near resonance creates a gravitational conversation between them that plays out over about 900 years. Their orbits breathe in and out, getting slightly more eccentric and then less, trading energy back and forth. But the key insight was that it's periodic. It comes back. Laplace declared the solar system stable, and for a while, everyone breathed easy. But Laplace had only proven stability to a first approximation. He'd used a mathematical technique called perturbation theory, where you treat the gravitational pulls between planets as small corrections to their otherwise perfect Keplerian orbits. And that works beautifully for short timescales, even for thousands of years. But what about millions, billions? The problem is that those small corrections can accumulate. They can resonate with each other in unexpected ways, and proving that they don't, proving that no combination of tiny nudges, repeated over billions of orbits, will ever push a planet out of its lane. That turned out to be one of the hardest problems in all of mathematics. The person who made the deepest early attempt was Henri Poincaré, around 1890. King Oscar II of Sweden had actually offered a prize for anyone who could prove the stability of the solar system, and Poincaré's entry was so brilliant that he won, even though he didn't actually prove stability. What he showed instead was something more profound and more disturbing. He demonstrated that in systems with 3 or more gravitating bodies, the trajectories could be so sensitive to initial conditions that they became effectively unpredictable over long timescales. Tiny differences in starting positions, differences so small you could never measure them, would eventually lead to completely different outcomes. This was, in essence, the discovery of chaos, deterministic chaos, where the rules are perfectly known, but the outcomes are practically unknowable. Poincaré had found it lurking in the heart of celestial mechanics decades before anyone used the word chaos in this technical sense. Now, chaos doesn't necessarily mean instability. This is an important distinction. A system can be chaotic, meaning you can't predict exactly where everything will be in a billion years, and still be bounded, meaning nothing flies off into space. Think of it like shuffling a deck of cards. You can't predict the exact order after 1,000 shuffles, but you know all 52 cards will still be in the deck. The solar system might be like that, chaotic in its details, but stable in its broad structure. Or it might not. That's the question. The real breakthroughs came with computers. In the 1980s and 90s, researchers finally had the computational power to numerically integrate the orbits of all the planets forward and backward in time over billions of years. And the results were eye-opening. Jacques Lascar, a French astronomer working at the Paris Observatory, published landmark studies in 1989 and through the 90s showing that the inner solar system, Mercury, Venus, Earth, and Mars, is genuinely chaotic. Not might be, not theoretically could be, but is. The Lyapunov time, which is a measure of how quickly small uncertainties grow, is only about 5 million years for the inner planets. That means if you nudge Mercury's position by just 1 meter today, after 5 million years, you've completely lost track of where it will be. After a few tens of millions of years, the uncertainty has grown so large that you simply cannot predict the detailed orbital configuration. The solar system forgets its own initial conditions. But here's where it gets really interesting, and, depending on your perspective, either reassuring or mildly terrifying. Laskar and later Gregory Laughlin and others ran thousands of simulations, slightly varying the starting conditions each time, and tracked what happened over the remaining lifetime of the solar system, roughly 5 billion years until the sun becomes a red giant. In the vast majority of those simulations, nothing dramatic happens. The planets wobble, their eccentricities drift up and down chaotically, but they stay in roughly their current orbits. The solar system is what you'd call metastable. Stable for now, stable almost certainly for the next few billion years, but not provably stable forever, almost certainly, because in about 1% of Laskar's simulations, roughly 1 in 100, something goes badly wrong, and the culprit is almost always Mercury. Little Mercury, the smallest planet, the one closest to the sun, the one whose orbit is already the most eccentric and most inclined. In those unlucky simulations, a resonance between Mercury and Jupiter slowly pumps up Mercury's orbital eccentricity over hundreds of millions of years until Mercury's orbit crosses Venus's. And once orbits start crossing, you're in genuine danger. In some of those scenarios, Mercury collides with Venus. In others, Mercury gets ejected from the solar system entirely. In a few truly dramatic runs, the destabilization of Mercury's orbit perturbs the other inner planets so severely that Mars gets flung outward and Earth's orbit becomes dangerously eccentric, not enough to eject Earth, necessarily, but enough to make it uninhabitable, swinging between scorching close approaches to the sun and frigid distant ones. Think about what that means for a second. There's roughly a 1% chance, over the next 5 billion years, that Mercury will destabilize. 1% sounds small, and it is. You should not lose sleep over this, which is ironic given what we're doing right now. But it's not zero. The solar system we live in, the one that seems so orderly and clockwork-like, is balanced on a knife edge of chaos that we can only see when we look billions of years into the future. Newton's clockwork universe turns out to be more like a spinning top that's very slowly, almost imperceptibly, wobbling. And this connects to something deeper about how we understand dynamical systems in general. There's a beautiful piece of mathematics called the CAM theorem, named after Kolmogorov, Arnold, and Moser, developed through the 1950s and 60s, which says that for systems that are close to integrable, meaning close to perfectly solvable like two-body gravity, most orbits remain stable even when you add small perturbations. Most, but not all. The theorem guarantees islands of stability in a sea of potential chaos, but it also admits that some orbits, the ones near resonances, can wander. The solar system lives in this mixed regime. The outer planets, Jupiter, Saturn, Uranus, Neptune, are deep in a stable island. Their orbits are so massive and so widely spaced that they're essentially locked in for the life of the sun. The inner planets are closer to the edge of that island, and Mercury is right on the boundary, flirting with the chaotic sea. What's remarkable is that the solar system has survived 4.5 billion years already in this configuration. That's not an accident. It's a selection effect. Early in the solar system's history, there were almost certainly more planets, more protoplanets, more things in crossing orbits, and most of them collided or got ejected. The ones that survived are the ones in stable or near stable configurations, because if they weren't, they wouldn't still be here. The solar system we see today is the winner of a brutal gravitational elimination tournament that played out in the first 100 million years or so. The late heavy bombardment, the formation of the moon from a Mars-sized impactor striking Earth, the possible ejection of a fifth giant planet, all of these events were part of that chaotic settling process. And this brings up something called the Nice model, named after Nice, France, where it was developed, not because it's pleasant, though it is rather elegant. Published around 2005 by Tsiganis, Gomez, Morbidelli, and Leveson, the Nice model proposes that the giant planets didn't form in their current orbits. They started much closer together and much closer to the Sun. Jupiter was a bit farther out than it is now, Saturn was closer in, and Uranus and Neptune were significantly closer, maybe only about half their current distances. And then, roughly 600 or 700 million years after the solar system formed, Jupiter and Saturn crossed their 2-to-1 orbital resonance as they slowly migrated due to interactions with the remnant disk of planetesimals. That resonance crossing was like a bomb going off. It destabilized the entire outer solar system. Uranus and Neptune were scattered outward into the Kuiper belt, plowing through it and sending comets and asteroids flying in every direction, inward toward the inner planets, outward toward interstellar space. This, the model suggests, is what caused the late heavy bombardment, the spike in impact craters visible on the Moon and Mercury around 3.9 billion years ago. The Nice model is still debated in its details, the timing, whether the bombardment was really a spike or more of a gradual tail-off. But the core idea that the giant planets migrated significantly from their birth positions is now widely accepted. And it means the solar system's current architecture isn't primordial. It's the result of a dramatic rearrangement, a gravitational crisis that the system barely survived. The planets we see in their current orbits are like furniture that's been shoved around the room during a fight and then left wherever it landed. So when you look up at the night sky and see the planets tracing their steady paths, know that what you're seeing is the calm after a storm. A calm that has lasted billions of years and will almost certainly last billions more. But underneath that calm, in the mathematics, there's a whisper of chaos, a faint, slow drumbeat of uncertainty that even our best computers can only track so far before the predictions dissolve into probability. And that's not a failure of science. That's a discovery. One of the most profound discoveries in the history of dynamics, that determinism and predictability are not the same thing, that you can know every law perfectly and still not know the future. Which is a good place to think about something else we've learned about our solar system. Not just how it moves, but how it fits into the larger story of planetary systems throughout the galaxy, and what the discovery of thousands of exoplanets has taught us about just how unusual or how ordinary our little corner of space really is. Because for most of human history, we only had one example of a planetary system, ours. And when you only have one example of anything, you can't help but assume it's normal. It's like growing up in one house and thinking every house has the same floor plan. You don't question it, because you've never seen the alternative. That changed on October 6, 1995, when Michel Mayor and Didier Queloz, two astronomers at the University of Geneva, announced that they'd found a planet orbiting a sun-like star called 51 Pegasi, about 50 light-years from Earth. And this planet was weird, really weird. It was roughly the mass of Jupiter, a gas giant, but it was orbiting its star in just over 4 days. 4 days. Jupiter takes nearly 12 years to complete one orbit. This thing was closer to its star than Mercury is to the Sun, and it was enormous. Nobody expected that. The theorists had spent decades modeling how planetary systems should form, and every model said the same thing. Gas giants form far from their star, out where it's cold enough for ice and gas to accumulate, and rocky planets form closer in. That was how our solar system worked, and so that was assumed to be how all systems worked. And then 51 Pegasi b showed up and broke the mold completely. They called it a hot Jupiter, which is a wonderfully descriptive name. A gas giant parked absurdly close to its star, baking at temperatures that would vaporize lead, and the initial reaction from a lot of the astronomical community was skepticism. Some people thought Mayer and Queloz had made a measurement error, that they were seeing some kind of stellar pulsation, rather than the gravitational tug of a planet. But the data held up. Other teams confirmed it. And within a few years, more hot Jupiters started turning up around other stars. Then came planets in wildly elliptical orbits, planets orbiting in the opposite direction from their star's rotation. Systems where multiple large planets were crammed into tight orbits. Systems where a giant planet orbited closer to its star than Earth orbits the Sun. The zoo of exoplanets that emerged over the next decade was so strange, so diverse, that it forced a complete rethinking of how planetary systems form and evolve. And here's what's really striking about this. Remember the nice model, the idea that Jupiter and Saturn and the other giants migrated from their original positions? That was partly inspired by the exoplanet discoveries. Because once, astronomers saw that hot Jupiters exist, gas giants that clearly didn't form where they currently orbit. They realized that planetary migration isn't some exotic edge case. It's common, maybe even universal. Planets form in a disk of gas and dust, and while that disk is still around, the gravitational interactions between the planet and the disk can cause the planet to spiral inward or outward. Some planets migrate gently and stop. Some migrate all the way in until they're practically kissing their star. Some get flung out entirely through gravitational encounters with other planets. The story of any given planetary system isn't just about where things formed. It's about the whole chaotic journey from birth to whatever configuration survives. The tool that really blew the doors open was NASA's Kepler Space Telescope, launched in 2009. Kepler stared at a single patch of sky in the constellation Cygnus for years, watching about 150,000 stars simultaneously, looking for the tiny dip in brightness that happens when a planet crosses in front of its star from our point of view. It's called the transit method, and the dip is absurdly small. For an Earth-sized planet crossing a Sun-sized star, you're looking for a dimming of about 1/100th of 1%. Kepler was sensitive enough to catch that, and the results were staggering. By the time the primary mission ended, Kepler had found over 2,000 confirmed exoplanets and thousands more candidates, and the statistical analysis of those detections told us something profound. Planets are everywhere. On average, there is at least one planet for every star in the Milky Way. That's at least 100 billion planets in our galaxy alone. Probably more. But the really interesting part isn't just that planets are common, it's what kinds of planets are common. And this is where our solar system starts to look a little unusual. The most common type of planet Kepler found was something we don't have, a super-Earth, or sub-Neptune, depending on how you want to classify it. These are planets bigger than Earth but smaller than Neptune, roughly between 1.5 and 4 times Earth's diameter. They're incredibly abundant around other stars. Some are probably rocky with thick atmospheres. Some might be mini gas planets with no solid surface at all. Some might be water worlds, covered in global oceans hundreds of kilometers deep. We don't know for sure because we can't study most of them in detail yet. But the point is, this size category, bigger than Earth, smaller than Neptune, is the most common kind of planet in the galaxy, and we don't have a single one of them. In our solar system, there's a gap. You go from Earth, the largest rocky planet, straight up to Neptune, which is about 4 times Earth's diameter and 17 times its mass. Nothing in between. That gap, which seemed unremarkable when we only knew about our own system, now looks like it might be the strange thing, the thing that needs explaining. And then there's the architecture. Many of the multi-planet systems Kepler found have a very different layout from ours. They tend to have several planets of similar size packed into tight, compact orbits, often closer to their star than Mercury is to the Sun. These systems are sometimes called peas in a pod because the planets are so uniform, similar sizes, evenly spaced, like beads on a string. Our solar system, with its mix of small, rocky worlds close in, a big gap where the asteroid belt sits, and then enormous gas and ice giants far out, that's not the typical arrangement. It might not be rare exactly, but it's definitely not the default. Now, you might be thinking, does that mean we're special? And the honest answer is, we don't know yet. There are huge observational biases in exoplanet detection. The transit method is much better at finding planets that are close to their stars, because those planets transit more often and block more light relative to their orbital period. A planet like Jupiter, far from its star with a 12-year orbit, is very hard for Kepler to detect. You'd need to watch for decades to see enough transits. And a planet like Earth, small and in a roughly 1-year orbit, is right at the edge of what Kepler could reliably find. So the catalog of known exoplanets is heavily skewed toward large planets in short-period orbits. The systems that look most like ours, small, rocky, planets close in, gas giants far out, lots of empty space in between, are exactly the kind of systems our current instruments are worst at detecting. So it's entirely possible that systems like ours are common, and we just can't see them very well yet. That's starting to change. NASA's TESS mission, the Transiting Exoplanet Survey satellite, launched in 2018, is surveying nearly the entire sky rather than staring at one patch, finding planets around brighter, closer stars that are easier to study in detail. And the James Webb Space Telescope, which began science operations in 2022, can analyze the atmospheres of some exoplanets by looking at starlight filtering through them during transits. That's spectroscopy again, the same basic technique that Kirchhoff and Bunsen pioneered in the 1860s, the same method that revealed helium in the sun before anyone found it on Earth. Now it's being used to detect water vapor, carbon dioxide, methane, and other molecules in the atmospheres of planets orbiting other stars, light years away. There's a beautiful continuity there. The tools change, the distances grow almost incomprehensibly vast, but the underlying principle, that light carries information about what it has passed through, that hasn't changed since Fraunhofer first noticed those dark lines in the solar spectrum 2 centuries ago. And what everyone wants to know, of course, is whether any of those planets could harbor life. That question is still wide open, but the search has narrowed in interesting ways. We now know that rocky planets in the habitable zone, the region around a star where liquid water could exist on the surface, are not rare. Statistical estimates from Kepler data suggest that something like 1 in 5 Sun-like stars has an Earth-sized planet in its habitable zone. In the Milky Way alone, that's billions of potentially habitable worlds. Whether any of them actually are habitable depends on so many other factors. Whether they have atmospheres, whether those atmospheres are the right composition, whether they have magnetic fields to shield them from stellar radiation, whether their orbits are stable enough over billions of years. All the things we've been talking about throughout this whole journey, atmospheric chemistry, magnetic fields, orbital dynamics, gravitational stability, they all converge on that one question. And maybe that's the most beautiful thing about studying the solar system. It's not really one subject. It's everything. It's gravity and light and chemistry and time. It's the physics of gases under unimaginable pressure and the delicate balance of a planet's distance from its star. It's the story of how dust becomes worlds, how worlds find their orbits, how some of those orbits last and others don't. It's the story of people too. Kepler poring over Tycho's numbers by candlelight, Newton sitting alone inventing the mathematics of motion, Herschel stumbling onto a planet he thought was a comet, Tombaugh blinking between photographic plates looking for a dot that moved, Vera Rubin and others revealing that most of the universe's mass is something we can't even see. It's engineers building spacecraft that survive for decades in the void, sending back data from places no human eye has ever directly witnessed. Think about the Voyager probes for a moment. Voyager 1 and Voyager 2, launched in 1977, are still out there. Voyager 1 is now over 15 billion miles from Earth in interstellar space. It crossed the boundary of the Sun's magnetic influence, the heliopause, in 2012. It's the most distant human-made object in existence, and it's still sending data back, faint signals that take over 22 hours to reach us at the speed of light. The power source is a lump of decaying plutonium-238 that generates less electricity than a dim light bulb, and the onboard computer has about 70 kilobytes of memory, thousands of times less than the device you might be listening to this on. And yet it reshaped our understanding of every planet it visited. It discovered active volcanoes on Io, revealed the complexity of Saturn's rings, found new moons, measured magnetic fields, and took that famous pale blue dot photograph of Earth from beyond Neptune's orbit. A tiny speck of light suspended in a sunbeam, everything and everyone you've ever known captured in a fraction of a pixel. That photograph was Carl Sagan's idea. He campaigned for years to get NASA to turn the camera around and take it. And when he wrote about it, he said something that I think captures the spirit of everything we've been talking about tonight. He pointed out that on that tiny dot, every human being who ever lived out their life. Every act of kindness, every war, every invention, every moment of wonder and every moment of despair, all of it happened on that mote of dust suspended in a sunbeam. And you know, lying here in the dark, thinking about all of this, the orbits and the forces and the billions of years and the billions of miles, it can feel overwhelming. But I think there's something deeply comforting in it, too. The same gravity that holds you gently against your bed right now is the force that shaped every orbit, sculpted every ring, pulled every planet into being. The atoms in your body were forged in stars that lived and died before the sun was born. You are, in the most literal and unsentimental sense, made of the solar system, made of the galaxy. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now. All of it was cooked in the cores of ancient stars and scattered into space when those stars exploded and then gathered up again by gravity into a new cloud, a new disk, a new system, a new world, and eventually, somehow, into you, lying here, listening to this, thinking about planets. The solar system is still out there doing what it's been doing for 4.5 billion years. Jupiter is still sweeping up debris, still protecting the inner planets with its enormous gravity. Saturn's rings are still shimmering with billions of ice particles, each one in its own tiny orbit. Mars is still slowly losing what's left of its thin atmosphere, molecule by molecule. The Kuiper Belt is still full of frozen worlds we haven't visited yet, and the sun is still burning through its hydrogen, steady and reliable, with about 5 billion years of fuel left. Plenty of time. So let all of that settle. Let the orbits slow down in your mind. Let the numbers and the names and the dates blur together into something softer. Just the feeling of how vast and old and patient the solar system is, how it was here long before anyone looked up and wondered about it, and how it will be here long after. The planets don't need us to understand them in order to keep moving. But isn't it something that we figured out as much as we did? That we worked out the shape of orbits from a small rocky planet, using nothing but light and mathematics and stubbornness and time? That's enough for tonight. The solar system will still be there in the morning. And so will you. Rest now.